So we are talking of flexible payments, and of course we know that they are constructed with top layers of bituminous material, and naturally between the subgrade and the bituminous layer there are granular layers actually. Other way of looking at it is they are also called as unbound granular layers. Binding means binding could be, as we said already, bitumen, or of course in the rigid payments it's going to be cement actually. So popularly in the pavement terminology, they are called as unbound granular layers. Bound means bituminous kind of thing. Then we have, of course, design methods now. These methods are based upon, in the beginning, it was empirical methods. Some of them, in the beginning, was based upon soil classification. Then the CBR method got evolved. I will tell you later what is the basic context in which CBR method of testing and CBR the design was evolved actually. Then there are some methods also based upon basically C and 5. That means, we are trying to use the same kind of bearing capacity system of Terzaghi, wherein there's a cone formed between the foundation structure and the soil, and that is going down. So a extension of that is made by using the same C5, but somehow that is not acceptable to pavement engineers, so that got discontinued. And then, of course, the methods which are there is what we call as limiting deflection method. Limiting deflection method means, okay, they said the deflection of the surface is limited to something, and deflection of the subgrade is limited to something like that. There is limiting deflection which is there. Actually, in principle, we are following the same thing. We are now calling it limiting strain, both the tension strain, tensile strain below the bituminous layer, and the top we are calling as in the vertical strain. So this method led to what we, of course, seen as the mechanical empirical method. And so what was there is, these are theories only. Basically, they are theories. Actually, the CBR, which is not really theory, it was based upon some testing and evolving a new methodology in those days now. Others are theory only. But what really happened was these theories purely never worked actually. But then, so we need an observed performance and theory to prove that things are matching actually. And so a realistic design of payments is really having both these components. That's why we said mechanical empirical method. Now, before we go further into the flexible payments now, let us quickly see the concrete payments also, how they are composed of. I think you remember that the majority of the payments are of PCC, plain cement concrete, and then of course they are jointed. And what is it we are trying to do? We are trying to have a block actually. So a number of blocks are there. So you assume that this is one lane and this is one lane, second lane. Now what is width of a lane? Anybody remembers? Lane width? Anybody remembers the lane width? Okay, it's 3.5 meters. So this is 3.5 meter wide and this 3.5 meter wide. Two lanes are there now. And we also take a length of this also, sometimes as 4.5 or anyway, it's between 3.7 to 6.1. I think in India we take as 4.5. So there is a standard on that now. So we take this slab actually, which is a plain concrete slab. So then between the adjacent slabs now, we have basically a longitudinal joint and also we have a cross joint actually. Lateral joint you can say, or transverse joint you can say that now. And what is happening is, when the vehicle is moving from one slab to other slab now, naturally there is a stress transfer between this to this now. Particularly when it's coming to the edge of this a single block now, a block of plain concrete, naturally maximum stress is going to be there, and it's a combination of wheel load stresses and the temperature stresses now. Anyway, it is weakest at the junction, let us say, and so to transfer the loads effectively, we create actually a load transfer system. So that is given by a double bar. So that is a double bar gives us this. A double bar gives us that kind of facility. So double bar is actually a load transfer device. So depending upon how we calculate stresses now, we have a frequency of the double bars now, spacing and all. So there's a system for that. If you are interested, we can deal with that also. And then these are actually also joints between one lane and other lane actually. They are the longitudinal joints now. So sometimes they can be, the slabs can warp also. That means the whole slab on this side and other side can warp themselves. So to prevent that warping now, there are joints now. So these joints also have some reinforcement in between joining them now. So they are called as tie bars. So double bars are low transfer devices. Tie bars are not necessarily like that now. Okay, so tie bars are coming from lane to lane, let us say, and the double bars are actually coming from in the same lane from block to block actually. So that is what we are trying to say. In the section now here we see that this is a double bar actually because the low transfer view that way, and that is what we have to keep thinking. So again, a three-dimensional view of the same thing now, and between the two lanes now, we have these bars, which is a tie bars now, and all across here between one block and other block now, there are these double bars. Okay, so below this slab and above the subgrade, there is also what we call as a base or subbase. Always this is a base or subbase. I will talk more about that later when we deal with it if time permits. Otherwise, in the original way of designs actually, for design of the pavement, they were only considering the presence of the subgrade only. That means they are considering the modulus of that. So modulus of that only is taken actually, and then design is done now. And this layer of base subbase, which is of course granular, that means made of stones only, that was only supposed to be facilitating the construction of the pavement, construction of the concrete portion of it, and also to allow drainage now. It was not a structural layer. Today it is a structural layer, and it has got a lot of thickness, and even that also got two layers now. We will see more of it as we go further now. So then that was the what we call as plain concrete pavement, jointed plain concrete pavement, and again it is giving you one more expectation of it now. One is that even though the blocks have got low transfer devices now, naturally in summer they may expand. So if each of the blocks is just next to each other now, naturally they are going to get crushed. So there will be always an expansion joint actually between the blocks. Okay, in the same way, it can contract also. So we also have now, apart from these general joints, which is said for double bar and for tie bar now, we also have expansion contract joints, and a third kind of joint is going to be obviously construction joint. So there are various kinds of joints now, and the diameters and the way we construct it. Suppose expansion joint means you should be allowed to expand actually. That means the so-called double bar which you are going to provide now is not fixed on both sides, fixed on one side, other side is and to be loose now, so that expansion occur. So there are a lot of details which you have to see. In fact, the so-called bad performance of these jointed plain concrete pavements is that we don't maintain the joints perfectly. From the design viewpoint now, what people very loosely say is that this joint we are doing now is supposed to be a design crack actually. The joint is a design crack. That means we initiate a crack. If you don't make any such joint now, make only plain slab now, obviously it's going to crack up actually. So instead of allowing the crack to occur wherever it is possible, wherever its maximum stress is there, we are trying to limit that, or we are going to see that it occurs only at these joints. So it is a designed weak plane actually. So then we have another kind of pavement. Yeah.
The difference between the expansion joint and the construction joint is only about the thickness of the joint.
No, many things are detailed. We'll talk of that later. We'll talk of that now. It's only thickness now.
Okay, sir.
Isn't it? What I'm saying is that we're talking about the function of that now. As of now, we're just a function of that. There is a difference, fundamental difference between double bar and tie bar. Okay, that is one difference now. And then there is a lot of differences between the expansion joint, contraction joint, and then one of them can be also what you call construction joint now. So detailing is going to be very important actually. We'll deal with that now. In fact, we design the details basically. Okay, so it's not something specific. It depends upon many things actually. And as I told you, the placement of double bars is also going to depend upon how the load is transferred actually, where the maximum stress is going to come now, are the reload stresses, are the temperatures now. Temperatures can be due to uniform expansion contraction and also due to difference in temperature. Oh, that's very interesting topic by itself actually. We can deal with it if you give me time. So the next, so this, whatever we discussed till now, I repeat, is jointed plain concrete pavement actually. Now, we also have such a pavement actually, but in this case, it's reinforced. These blocks are now reinforced. You see this now? At the somewhere in the center now, we have these blocks which are So at the center, you see the temperature steel here now. So at this area now, we find that there is temperature steel. So this is now reinforced concrete pavement, you can say, in simple sense. But in this case, only each block is reinforced. So that is what we covered at the beginning. At the top left-hand side, so that was the jointed plain concrete pavement now. On the top right-hand side, we have a jointed reinforced concrete pavement now. So here also joints are there. And you see here now, he has given some lengths also. You convert it divided by 3. So between 10 to 30 meters, the joint can be there actually. And usually, they are transfer joints with doubles. Okay. Now, there can be also continuous reinforcements. So this is a continuous reinforced concrete pavement now. So there are no joints at all. The reinforcement is continuous. It's like a slab resting on the ground actually, like a concrete slab resting on the ground. And some people prefer it because they see any joint means if you don't maintain joint perfectly by putting proper bitumen and other kinds of things and maintain the spacing between them, you jump between that. Now you always find, you remember, between whenever you go over a bridge now, between one slab and other slab now, that joint is there. So you jump over the joint every time. So disturbance is caused and you can't go with the speed which is designed. So some people don't like the joints at all. So in those cases, we can have a continuous reinforced slab also. So that can be designed without any problem, but it's more complicated than normal plain slab actually. The other kind of thing is that there can be also precast, pre-stressed. Okay, this is normal reinforcement, and here it is a precast concrete pavement now. So there are various types in this. The difference between this is normal reinforcement. This is actually pre-stressed reinforcement. So there can be theoretically 4 types now, but I can tell you that this particular one is the most common kind of thing. So then another kind of thing we should remember is very clearly that what are the kinds of stresses are going to occur now? Anybody remembers what you studied in UG? In a concrete pavement, any stresses, what kind of stresses are going to come?
Warping stresses.
And the temperature stresses.
Sorry?
Wheel load stresses and the temperature stresses.
So what are the temperatures like actually?
Like during summer, midday, and during midnight, what tension and compression occurs on the slab top or slab bottom, we check that.
Oh, that is nice. That is nice. But assume that the slab actually is just cast in the ground. Are there any stresses in that? The slab is just cast and cured also and resting on the ground. The stresses are only due to self weight if it all is there. Okay?
Yeah. Yes.
There is no stress at all on that now. Only when it starts moving along against the subgrade, there could be frictional stresses, let us say.
Frictional stresses.
Okay, frictional stress could be there. And then there is a difference in temperature of the pavement between the top and bottom. We divide into 2 zones. One is uniform temperature reduction and another is uniform temperature increase. Okay. And also differential temperature. That means the bottom can be, let us say, high temperature and top can be low temperature. So when the bottom is high temperature, naturally it's going to warp upwards or curl upwards now. Okay, when it's attempted to curl upwards, what is going to happen now? It will try to fall down by itself actually because of the weight. So the weight stresses are going to come. And if it happens that the wheel load is there also at the same point, naturally that combination is going to be worse combination. Okay, so it is actually causing a curling effect now. In the same way now, if the top temperature is more and the bottom temperature is low, then what is going to happen now? Naturally, if the wheel load is going to come on the top of that upward portion, on the heel portion, naturally there will be another kind of stresses. So this is what is going to make complicated because to estimate this variation temperature itself is a difficult task. So in IRC, of course, they say that in these zones you can assume this and this. And the LF friction stress is going to come because of the uniform movement of the entire slab actually. And because it is resting on the ground, naturally stress is there. But then imagine that it's not on the ground just for a minute now. If it is going to be a free body, there's no stress on that now. Maybe if you have a contact and expand now, there's no stress on this. But the stress is coming actually because it's resting on the ground. So that way it becomes very complicated kind of system. And naturally friction can vary because of mass content, because of freezing and all. Many things are there. And we have, of course, different kind of, not single load, we're also going to have different combinations of loads also. Okay. So in these combinations, naturally, we are worried also what is the shape of the contact area, about which we'll talk in this lecture itself now. So is it edge loading, is it interior loading, is it corner loading, are going to be three different kind of parameters which we are going to consider actually. The other thing which is going to come, very important basically, is going to be what we call as pumping. So what is pumping now? We said when we are going along the road actually, if you don't provide, let us say, any double bar, any load transfer device now, what is going to happen now? If it is joint is open between the two blocks, two plain concrete blocks now, so naturally when the wheel is going to come to the edge, when the wheel is going to come to the edge like this here, what is going to happen? It is going to cause a vertically downward movement, a cantilever. Very small. But then if it is going to be monsoon time, and if the water is going to come along, the joint space onto the subgrade, then what's going to happen now? The first time it's going to come and rebound. Second time it's going to come and rebound. So number of the cycles of movement of the vehicle, movement of the wheels actually, is going to make this soil as a slurry now. Water is there, and then repetitions of compression, expansion is going to cause slurry now. And slowly, even if there's no more water coming in, the slurry will keep going out actually. The slurry will start going out. When once going out, that means a vacancy is being created here now. So what's going to happen now? Earlier the movement is only restricted to the edge of the slab now. So slowly, more and more fines are getting out as slurry. So naturally, somewhere it's going to finally crack up now. So this is something this is what we call as pumping. And more often than not, if you carefully see in some of the roads which are on poor subgrade, naturally you find from the edges, slurry coming out actually. You may watch in monsoon time when you go in a car or when you watch a truck actually traveling, sometimes through the edge slurry keeps coming out, water comes out initially. So there's a very dangerous situation now. So one reason why we are providing this, in this double C is to see that there's a load transfer, number one. And we have to maintain the joints. If you don't maintain the joint, water is going to come inside. So the problems are going to come now. Okay, the suction is going to come. So this is very severe kind of phenomena which we have to prevent. The second important point we are going to say is that I mentioned that we got a truck tire and we got a aircraft tire now. So the truck tire has got basically a tread. A tread meant, obviously all of you have seen a scooter tire also, any tire is like this now. That means there is a projected portion. There is always a projected portion actually. And then the other portion is inside. So this projected portion is usually made of only rubber. Okay, it could be synthetic rubber also. And then there is a inside, the actual periphery of the tire is different. It is actually reinforced with material of high strength basically. So there's a got radial tire and many things are there. The tire design is a complex subject right in textile technology also. Anyway, we are looking at the surface which is in contact with the ground or with the contact with the pavement now. So there is a very interesting study done by Crony in 1977. In fact, there's a classic book, Crony and Crony wrote actually, published by the HMSO in UK, after a lot of experience of measurements and things like that, by the Transportation and Road Research Laboratory at Crathorne, UK. It's a government laboratory. And so in this case now, what is it which is done is that they have taken a load, 2290, 1542, like this now. So the manufacturer rating, of course, is 100. Okay, manufacturer rating is 100. That is exactly 100% of whatever is there now. So the rating is 1542. So the tire imprint is going to be like this. Okay, if we are reducing that to 2/3 of the load now, the tire imprint is going to be like this. It's different now. If you are reducing to 32% of the rating, the load it can take, it is going to become circular now. And here you see that now, if you are overloading it by 50%, 150%, so you find that this imprint of the tire on the ground, on the road surface is going to be almost, you can say, rectangular now. So these two appear like a kind of ellipse. This appears like a circle now. So you see that now it's very difficult to even find out the actual shape of the contact area. So there are different assumptions which are made in the flexible pavements and the rigid pavements also. We'll see when we go further on onto that now. So that is the advantage. What is that which is going to do? The treading is going to do? It is going to create more friction between the pavement surface and the tire actually. That is purpose now. So when once these threads become, very thin, what we do retreading. Retreading actually, we give it to an agency, they do retreading, and then we can reuse this tire for some more time. So that is one thing we have to remember actually. Other thing is that there is a numbering which is done to the tires also. So supposing we have this first number 195 is the width of the tire in millimeters, and 55 is what is it? Is aspect ratio or tire profile, this much above the rim actually, and R means the radial construction. Radial will see that, and 16 is the diameter of the wheel rim in inches. This is the wheel rim. So that's how the what you call the tire is specified. So when you take a vehicle for getting a new tire or something like that, now the mechanic looks at your tire actually, or the vehicle, and say, okay, I buy a allow number. So we should know this. This is what is. So what is now radial construction? Now, if you see, of course, you may not be able to see this also because in almost all the modern vehicles now, you are somehow there a feeling that the tire is, there is a tire pressure is very less. So that means they become kind of flat at the bottom, and then at the edge now you find there's some kind of compression. The air is projecting outside actually, and we feel that the air pressure is less. No, it's not like that. That is the way in which the tire is made actually. That it's going to expand at the later stage. So by that process now, later we'll see also in what we call as geotubes also, we find that the contact pressure is not going to be the same. What did we say earlier? We said there is a tire load on the tire, load on the wheel, and that will be naturally transferred onto the pavement by a contact now. So what we are saying is that this contact is going to be not contact pressure positive, it's going to be negative also. There is suction at the edge actually. There's a negative contact at the edges, that means less pressure is there, and the tire also, and on the contact also. So that is more confusing. But one thing we can really say is that now the contact area is going to change depending on the way you calculate actually. So the contact area thinking in the side on the y-axis is going to be contact area in, I think, millimeter square or whatever it is, millimeters into square millimeters into 10 to the power of 2, and then on this side is the wheel load now. So you see what are the three components now. So one, I think the topmost is area computed from wheel load and tire pressure. So wheel load we know, tire pressure we measure. You go to any petrol pump, they will give you what is the tire pressure now. So if you are trying to plot that now, so this line is going to be, the first line is going to be like this. This line is going to be the first line actually. Okay. And area of the contact envelope now. That means if you are trying to draw an envelope of the contact area, we have said, for low loading it is a circle, and then for the heavy loading 150% it's going to be a rectangular now. You are going to get basically the second curve now. Okay. The third curve is going to come when you find out the actual contact area. That means the rubber portion which is projecting, which is actually touching the ground, touching the pavement. If you calculate that actual contact area, we find that this is a kind of curve. We see that even just choosing the contact area means indirectly the pressure. We find we have got problems because we see this now when the wheel load in tons is going to be like this, 1 ton only. So we find that this is the kind of thing. And when you got higher wheel load, actually, this is going to be different now. Which one are we going to choose now? Are we going to choose the average area? Are we going to choose this area? Are we going to choose this area? So you always find that actually when the contact is less now, the aerial contact is less only anyway. Contact area less means the pressure is going to more. So we normally make an assumption that the tire pressure is equivalent to contact pressure. This is just to show that it is not equivalent. Okay, you should remember that as we go further. The second, of course, is we are talking of either stage construction or maintenance of the road now in general. So when you think of a design, let us say, so we are talking of, let us say, traffic in years. Okay, and then what is the required thickness now? What we mean is that now, if you think that we are going to have, say, some 5 years or whatever it is now, the traffic is going to be this much. Thickness is going to be this much. If you think of, let's say, 10 years, then maybe thickness required is this much. So the curve is going to obviously increase the traffic, no doubt on that now. But the traffic is going to be generated over years. It's not coming suddenly now. So what we do is now, we are designing, let us say, for 10 years, the same thickness, P1 or whatever it is now. Then what we do, we put a resurfacing or strengthening of this road. And then by resurfacing, we have design now, We are designing for Y2 years. Y2 years meant actually more axles coming in, which are estimated on this now. So we try to see what is the condition of the road at the end of I1, here, and then whatever traffic we are going to generate for the next few years for design life, we are going to put the required thickness as per design principle. So then it goes on for some time. Then of course we do some resurfacing. So this is a policy which you are going to think, no, I am not going to run this road for next 5 years now. That could be one thing. Other people say that, okay, every 2 years, 3 years, we are going to improve the surface and things like that. Road condition is going to be all right now. Less water is going to come into that now. So the question of now, is it almost annual maintenance, and every 5 years or 10 years is going to be major maintenance now. Okay, so this has to be always what we call as payment management system. So which is a function of the time. Of course, in the time we are going to say this is the kind of number of movements and number of axes are going to travel now, and then you take a call on how do you want to design actually. So other same thing we are going to do in terms of age now. So if you think that when you consider the road in the beginning, whatever road you are going to consider, bituminous or concrete road, whatever it is now, in the beginning it's going to have excellent serviceability. What do you mean excellent serviceability? It means it's going to be very smooth. Let us say smooth means it's not frictionless, something like that. Now the surface is generally good now. The camber is good. Everything is good. No cracking and things like that. So there are measures for measuring serviceability. As for Astro, we'll see that tomorrow. So serviceability is, let us say, topmost. So if you think of let's say 0 to 5 now, maybe in a expressway, I will put it this serviceability, what we call as initial serviceability, as 4.5 in a scale of 0 to 5. Okay, after having done that now, naturally when you start using this road, this serviceability is going to decrease. It will start developing cracks and have raveling. It will have some potholes, and so slowly it's going to come down now. And you want to come down to 0, which is impossible, or you want to stop it somewhere actually. No, at this point I'm going to maintain. So that's what I call a routine maintenance. So if you keep maintaining routinely, so naturally the decrease in serviceability is going to be less, and so the level is not going to be so much down. It will be what we call as terminal serviceability. At the end of the design period, this will be the condition. If I assume that this is going to 4.5, I can say that for a state highway, I will allow up to 2.5. If it is going to be, let us say, expressway, then I will only allow up to 3.5. That means the serviceability is going to be always between 4.5 to 3.5 only, not come down actually. That's how we are going to maintain it now. So once you have come to the stage now, we do a major maintenance now. So till now, we are doing a routine maintenance that may fill in the cracks or filling in the rut holes or ruts and things like that. Now we can keep doing those minor maintenance or annual maintenance. And at the end of that serviceability period, I mean the minimum serviceability which you are designing, which you are choosing by design, and then of course we reconstruct the road again, assess the condition of the pavement, and then increase thickness depending on what you want. Now then keeps going on. So these are the management principles which you have to follow systematically if you want to maintain a road under good conditions. The other thing which you are always going to think of it is, we can think of in a simple fashion. If you increase the wheel load, obviously on one side, wheel load is increasing, and then naturally the pavement thickness is going to increase. That means you can be having this kind of curve. This kind of curve is going to be for a given subgrade strength, be it CBR or maybe some of the modulus. So we are going to have this kind of variation. That means now higher the wheel load, naturally higher is going to be thickness required. That's common sense. Okay, now if the subgrade strength is going to be higher, naturally we are going to have the full line, thick line. If the subgrade strength is going to be low, we are going to dotted line. That means we are going to require more thickness for poor subgrades. That is obvious. So we can think of a constant volume of traffic. We can think of equivalent swing wheel load, and then this concept is essentially used in airports. Okay. Whereas we have a fixed standard wheel approach, which is called as equivalent wheel load factor, EWF. So what is it we are going to do is, in this case, we are going to talk of repetition failure. As I told you, we are going to think of millions of stand axles now. So we are going to have repetitions to failure on x-axis and pavement thickness on this axis now. So normally what is going to happen now, for a given condition, we are going to have more repetitions to failure. That means more design life actually. We are going to have more thickness. Okay. And if the subgrade is poor now, naturally we are going to require more thickness. So whether you want to increase the wheel loads or increase the same, I mean, we have the same wheel load, but then repetitions. So repetitions are going to make a lot of difference in terms of highway payments. So earlier case was applicable to airport payments, wherein there are limited movements. We'll see that now. So then we can think of load equivalency factor also. The point is that we have trucks of various kinds. For example, if you just think of equivalence factor for, I'm talking of load equivalency factor. So a car will have hardly any load, just 0.307 in some units, let us say. That means the payment design is not done based upon the cars which are going to move on there. It's going to depend on freight or trucks which are going to move now. So light trucks is going to be 0.1. And then if you have heavier trucks, naturally this value is going to be 1.35, 1.85, 5.11, things like this now. It all depends upon that actually. So loaded 18-wheeler or 40-feet bus, 60 feet loaded articulated bus or trucks and things like that, they are all going to give you more and more loads actually, more and more loading factors. In place of that, we'll see now. So in a standard system actually, we have 80 kilonewton as a axle load with a dual wheel. That means the rear axle of a simple truck, simplest truck will be having 2 wheels, single axle. In the front now, it's going to have obviously again a single axle, but 1 tire only. Okay, so that is one which is going to allow you to maneuver over the pavement, and the main load is taken by the rear axle actually. So that is the standard axle actually, and the weight of that is going to be, the axle load is going to be standard value is 80 kilonewtons or 8 tons is defined as standard axle. So everything we are going to do in this business now. So then we can fix up actually what is this configuration of a different kind of axle, 16 tons, 40-ton truck, a light commercial vehicle, and 3-axle truck and 4-axle semi-articulated. Articulated obviously means that you see here now the initial driver, the driver fellow is going to sit in a separate carriage, and then this is actually a trailer now. The entire thing is a trailer now. So he can maneuver very easily. You see long vehicles actually maneuver very easily because this is fully articulated. That means it is fully free to move actually. Whereas in the semi-articulated now, this is almost, though there is some flexibility, but is directly connected to this now. Okay, in this case, of course, they are directly connected. So you find that depending upon the thing it is going to be there, we can have up to normally 40 tons. In mining and all, will have much heavier loads also. It can go 100 tons also in mining. But normal trucks are about 40 tons actually, unless they've got more axles, unless it's a very special vehicle for BHEL or certain, you can say, wind turbines and things like that. So it's a different system. So in all these cases now, we have number of axles actually. Each axle load can be defined. So when you have the single axle, single load, we'll say that 6 ton is legal axle load. And now, of course, the government of India, almost I think now 25 years, 30 years now, they said the axle load is going to increase. What is the standard axle load around the world? It is 88 kilonewton, 80 kilonewtons, 8 tons now. No, they said in India it's going to be 10 tons actually. And in fact, it's 10.2. We'll see that also. If it's tandem axle, that means 2 axles put together actually, the legal axle load is going to 18 tons. And then it is going to be tridem axle, that means 3 axles put together, it's going to be 24 tons. That's the legal axle load. So the normal one is going to be around 10 tons. Tandem axle, that is a single axle with the dual wheels. And if there are going to be 8 wheels, it's a tandem axle, 18 tons. If it is going to be 6 and 6, 12 wheels, actually, it's going to be tridem axle. Okay, so that is the way in which we have the loads which are going to be permitted. But you should remember that also, that I think probably a year back, the Minister of Road Transport and Highways, he just declared that the vehicles can be 20% overloaded. I don't know what it means, because they didn't fix up the wheel loads actually. They simply said on the whole it is going to be more, and they didn't revise the design methodology also. Obviously, when we are designing these roads actually for based on standard axles now, we have to take this decision with a pinch of salt. Okay, so this is what we said. I said 10 to 10.2 is normally what people try to use it now. So that is the basis of our loads, let us say, in highways. Then it comes to aircraft now. So what are the kind of loads now? We had till now up to 40 tons, which a vehicle can carry usually. So then, after all, the type of aircraft means a lot of things now. One, of course, easiest to be is piston engine. That is like flying club now. Maybe just a pilot only there. At best, you'll have one more fellow sitting next to him. They are very late aircraft now. They don't come into picture, but normal civil aviation. We are concerned civil aviation, wherein number of passengers who are paying are going to travel. So for that now, there are two classes of aircraft. One is turboprop. Turboprop means there is also a propeller and also there is a turbine. So you can see the propeller, both sides actually, two propellers on the aircraft actually. They are the ones who can carry from about up to 80 passengers actually. And they are the ones which are commonly used between small cities and things like this. And government has got some subsidy also. If you fly these smaller aircraft between two smaller cities now, that's called UDAN, UDAN, UDAN. And of course, major aircraft is going to be what we call turbojet. So thrust directly from the turbine engine. They are moving because of the turbines only. So naturally, this is a small vehicle. You can say small aircraft now. You are unable to see, but there is a propeller on either side of this aircraft actually. Okay, so we are not really worried about that. And we see larger aircraft now. They look huge now. So we are going to look at two things now. This aircraft is about to land. That's why the wheels are now coming out. Otherwise, during actual flight now, they are uplifted and they have become part of the main body of the aircraft now. Both the front wheels and rear wheels are going to be there. So, how do we classify these loads now, or the wheels will be loads now, into actual, you can say, design of the aircraft as well as the pavement now. So, these are what we call as the rear wheels actually, or what we call as main landing gear, because there is one set of wheels on one side of the aircraft, below the wing more or less, and other set of wheels on the other side actually. So there are, for every landing gear, there are two sides now. So in this case now, the landing gear consists of, you can see on one side there are 3 plus 3, 6 wheels, and other side 3 plus 3, 6 wheels. So that means main landing gear has got 12 wheels actually, and the nose gear usually single wheel. Okay, so who is going to take the load now? The main landing gear is going to take the load now, and the front wheel is actually going to take about 10%. That is the design way we're doing it. So the whole structure of the aircraft, if it's got, let's say, 100 tons, let us say, so 90% of the load, the 90 tons is taken by the main landing gear, and the nose wheel is going to take 10% load only. That is the basic way, but that is decided by the manufacturer of the aircraft itself. So aircraft may look like this now. There are several components of this. I think some of you travel by air should observe this actually. There are many components of this. We are not getting into all the details at this juncture, but then they look so huge now. And what we are interested in is actually what are the size of this plane actually. I mean both length, width, and wings and things like this, and of course the actual landing gear. So what we see now here is, in this case, the nose wheel has got at the center, we are able to see the nose wheel, and at the sides we are able to see the main landing gear now. So this is Airbus model A300-600 now. General dimensions, you can see that now. The edge of the wing dimensions across is going to be roughly 45 meters actually. The height of this from the ground is not specified, but the main landing gear distance is going to be 9.6 meters center to center actually. Okay, and you can see the rear actual tail, that also is going to be 16.26 meters away, and the central height also is going to be there. So if you talk of the same model aircraft now, model type aircraft now, the nose wheel, each of the wheel is going to be from center to center 0.625 meters, that means 62 centimeters away from each center to center, and the distance between the main landing gear and this is 18.6 meters, and of course again here in this case there are 4 and 4, that means 8 wheels are there. And what is it we are trying to do is that we are trying to see that the overlap between this side and this side is going to be minimum. That means there is no influence of this set of tires in this other set now. And so distance is 9.6 meters from center to center of the main landing gear, both sides. And the length, distance between these two in plan is 18.6 meters. And the pressure of the gears is going to be 12.4 kilograms centimeter square per each tire actually. I told you this is a ball tire basically, and the tire pressures maximum is 12.4. So what is pressures we are having for trucks now? It's a range of, if you talk of this, it will be about 3 to 4 kilograms centimeter square, that's maximum now. So the air pressure is going to be The tire pressure is going to be very, very high in aircraft, and the nose wheel is going to be have obviously slightly lesser pressure actually. Okay, and you also see the tire is different in size also. It's got a very specific tire for each of the aircraft. So what you find is that in the 1940s, the kind of loads which are going to have are very, very limited actually. It's all in pounds, I think. You see that from 1940 onwards, there is a terrible increase in the aircraft weights actually. So by about 2000 or 2005 now, we have reached this range of almost 1,300,000 pounds. Now, can the manufacturer keep increasing the, making the aircraft larger and larger? Any idea on this now? Can the aircraft manufacturer take a sumo decision? Okay, I'll make a new aircraft with heavier loads. Can he do this? Hypothetically, he can do it. But then the heavier aircraft now, depending on the kind of aircraft he's making, it requires longer length of runway. So you can always design a good aircraft, bigger aircraft, but it can't land on the existing airports. So he can only do with international connections, that means in contact with the ICAO. He has to also get a new runway design, that means runway length design, maybe width also, and all other facilities he has to create. So it's not a joke that we simply keep increasing the size or weight of the aircraft now. And so this has to be a win-win situation for both the aircraft designers or aircraft manufacturers and the airport authorities who maintain the systems for us. So that is something we have to keep in mind. So the size, as I said, keeps varying in a big way, different ways now, and it is almost fantastic now. So if you just see the Airbus 380, suppose we start from the right-hand side now, the A300 B2 type is about 304,000 pounds. Actually, it's American and the French one, it's always going to be pounds now. We divide by 2.2 to get into kilograms now. So roughly, if you divide by 2.2, what is that now? It becomes how much now? Assume that 3. So it's going to be 1 lakh pounds actually. That means 100 tons. Okay, kilograms. So you find that this weight is increasing continuously. A330 has got 469,000 pounds. A340 807,000 pounds. A380 1,305,000 pounds. And then if you look at Boeing, so Boeing actually, this particular model has got 870,000 pounds, 870,000 pounds, 41,000 pounds, 583,000 pounds. So the weights obviously are much more than normal trucks. Okay, that is first thing we have to see. The second thing we are going to observe is that it has to land on at an airport now. So the landing system we already know. It actually lands on a runway, and we have designed the length of the runway depending upon the location, its altitude, its temperatures and other things now. STP we got stand temperature and pressure actually. So depending upon the kind of aircraft now, each aircraft requires for the location now a runway of a given length and given gradient, things like that now. And once it lands, obviously it's going to move over a taxiway and finally comes near the apron, which is going to be near the terminal building now. So these are always 3 components of the airport. So this is the basic design actually. But in the design, what would say that though we are not going to consider here now, the runways or taxiways airport system should have proper drainage. For example, in the Bombay airport, we don't have such proper drainage. That means in a case of worst monsoon, the water can flow on the runway. When the water is flowing on the runway, it also brings with it some slush, some clay. So I already told you that the aircraft tire is barred actually. It is the surface of the runway which is going to be rough. Some projections are there in this now. If mud is going to come on the surface of the runway, obviously it becomes smooth now. Becoming smooth, obviously what it means now, we find that the length of the runway required is going to be more. So that is why you always feel that in monsoon conditions, we have to keep our fingers crossed when the aircraft land actually during severe weather conditions in Bombay, because that's how the airport is made. Maybe new Bombay runway is going to be different now. The other thing is that, so drainage is important along and across the runway and also in the neighborhood now. So drainage is important, the entire airport area. Then we also have some clearance required also. That means clearances for emergency landing and all, for arrival and departure. That's why you see that on either side now. There are also certain areas which are controlled basically, and that's why of course by common sense that I can't have a 10-story building at the end of runway. Okay, because it's going to oppose the actual inward or outward movement of the aircraft now. So these conditions, of course, we will not discuss too much on this now. You see that the runways configuration which you are going to have is going to vary. For example, I just show quickly certain pictures. Let's say this is in Alabama. You can see that now, almost like Changi Airport in Singapore. This is actually built partly in the sea, single runway. And what you find is that, let us say, Atlanta, one of the biggest airports now, has got, I think, numerous runways, numerous high-speed exit taxiways. Okay, and you can see aircraft are landing and departing continuously. So managing this is going to be quite this one. Now, in this case, you find also, particularly in the Atlanta now, maybe the direction of the runways are all going to be in the same direction. But if you go to, let us say, the New York airport now, it all depends on the conditions now. In certain weather conditions, the crosswind is going to more. If the crosswind is going to more, I think you might have been taught Windrose diagram also. So we should try to find out that 90% of the traffic has to be in one direction if the wind is like this. If it is not so, the Windrose diagram doesn't tell you this now. We have to have directions of the runways in two different ways actually. So in this case now, in the New York LaGuardia Airport now, so we have runways on across actually. One of them operating in one season, another of them operating on that season now. It all depends upon the crosswind direction actually. Again in Texas, we find almost two different inclinations you can say, or orientations, and the number of high-speed taxiways, high-speed exit taxiways. What do you mean high-speed now? So normally, the aircraft on landing, let us say, should be able to leave the runway very quickly. If it is going to take its own time to really come to a normal speed of say 70, 80 kph now, it will be occupying the runway for longer time now. So you should be able to exit very fast. If you exit very fast now, we need actually the taxiway at a smaller inclination now. That's where you can, let's say, take a turn at 120 kph also. So that's why you see that the crisscrossing is not just across, but these high-speed taxiways ensure that the runway is used by a single aircraft departing or landing actually for minimum time. So that's why you see there's so many runways and exit taxiways and normal taxiways and two directions because of the wind conditions. So another Charles de Gaulle Airport in France actually, again number of these things now you can see there's one set of runways on one side and the set of runways on side, all depends upon the space and the traffic and many things is going to be there. The airport design is very complicated kind of thing. Only very few consultants are there who can design the total system perfectly. Illinois, you go to Chicago in Illinois. So you find that again, the complex arrangement now. One, of course, is the runways and other things now, and there is the terminal building because dealing with millions of passengers every day, many things are going to require for this. In all these things now, we just talked of the general arrangement now. The number of runways is going to depend upon many things, of course, traffic. But one thing we are going to bother as engineers is, as civil engineers is going to be, what are the weights for which you are going to design? The aircraft doesn't have a standard weight. Okay, so what is it we are going to think of? First of all, we'll, let us say, talk of what we call as operating weight empty. The bottommost one, operating empty weight. What it means now, weight of the structure, weight of the aircraft now, the power plant in that, the furnishing, the systems, unusable fuel and other usable propulsion agents now, other items of equipment that are considered an integral part of a particular aircraft configuration. Also needed are certain standard items, personnel, equipment and supplies necessary for full operation, excluding fuel and payload. It's like dead weight, let us say. The dead weight of the aircraft now, any excess fuel it has to carry, and all the personnel required for that means including pilots and air hostess it is going to be there. All those standard things actually are all going to be included in operating weight empty. That's a basic weight of the aircraft. Then at the bottom they're going to hit now. It requires to add now the payload. That means is it going to be some freight or it's going to passengers now. And for its travel from a given city to city, it needs fuel now. Okay, we'll see that also. So with all these things now put together, we have a maximum takeoff weight. Maximum takeoff weight means the second one from the bottom. Maximum weight, otherwise at takeoff, brake release by the applicable government regulations and excludes the taxi and run-off fuel. So what it really means is that after taking its load, that means both fuel and the payload now, it is going to taxi to the runway end. So what is the weight it can take now at the juncture is what we call as maximum takeoff weight. So with this weight, it's going to take off now and then reach, let's say, from Delhi to Calcutta. And when it reaches from up to Calcutta now, it is actually already lost some fuel now. So the weight authorized for landing, which is called the maximum landing weight, is the weight which is authorized for touchdown or actual landing now. So these are the three things you have to remember now. So when taking off, it has got higher weight. When landing, it's got lower weight. But for our design, we are given one weight anyway, which is going to maximum takeoff weight. The other thing is, of course, seating capacity, cargo volume, usual fuel capacity, many things are there. So this is, of course, the arrangement of the wheels anyway. And again, in this case, the tridem arrangement basically. And another model now, the sizes are given. In the early days when I was writing the book, actually, all these were available now. You could write to Boeing and then they could send the brochures completely about what are the functions of aircraft, things like that. Now, all the pictures I have seen also are available in the normal net now. But I think slowly, after the incident in America, they started removing all of them actually. So I could get some data from the companies. So the point we're trying to say is a lot of things which are going to be there. So these weights now, for example, if I think of Boeing 707 now, maximum ramp weight, let us say for a model 120B is 258,000. And then, maybe kilograms is 117,100, that means 117 tons. Maximum landing weight is going to be 86,300, but takeoff weight is going to be, again, 117,000, that means 117 tons. So takeoff weight is 117 tons and landing weight is 86 tons. This is what we have to see. And you can see operating weight MT is 57.6 tons now. So what is the difference between these two things now? So from 57.6 actual operating weight MT, the maximum takeoff is going to be 117, which really means that 157.6 plus the payload, the actual passengers or freight is going to carry, plus the fuel, extra fuel. And when you talk of extra fuel now, the fuel is required for journey now, they always, by law, by ICAO law actually, International Civil Aviation Organization, they have to also carry enough fuel, not only from, let us say, from Delhi to Calcutta, but also if by some chance you can't land in Calcutta, the nearest airport, let's say maybe Bagdogra or maybe some other place, which it can take now. So it has to have the trip fuel, you can say, from Calcutta, Delhi to Calcutta, and then extra fuel to land if it can't land properly at Calcutta in some of the nearby airport. So all that has to be carried by the aircraft now. So that limits the entire capacity of this. So what you really find is that the aircraft has a capacity to travel longer. But if it's taking more weight of passengers payload now, naturally what's going to happen now? It will be taking less fuel only. So the same aircraft can, let's say, from here to travel London, but then it will take only small payload now. So that is what they have to, the aircraft operators have to decide what is it which is going to think, what is it is going to see, is the aircraft is going to operate long distance or short distance now. So that is what we have to really see. So these are also many things. What is the landing gear footprint, maximum pavement loads, landing gear loading on pavement, and requirements, as I said, from the ICAO and FAA. So all of them are going to be important for us to think of it actually. So these are, as I said, huge aircraft now on which they spend millions of dollars in making it and then operating it now. So I can pass on this letter to you. It's also in my book actually, and probably some of it you can get in the net also. So the landing gears are going to be the most specific for us from where we start working actually. And this is what we said actually. Initially, the simplest aircraft is going to have single tire gear, and the next one is going to be twin tandem. That means twin gear means actually on that side is going to be 2+2, and then tandem means actually on both sides is going to be more. So double dual tandem is going to be like this now. So this arrangement we have to see because we have to calculate what the stress on the pavement now. So normally what is happening is operating weight MT is about 40%, payload is going to be 14%, and then trip fuel is going to be 35%, and then fuel reserve to go to next airport if we can't land at the design place, 6%. So if the maximum gross takeoff weight is going to be so much now, payload, which really pays to them, is going to be 14%. That's why the operations of the aircraft is going to be quite expensive actually, because you can't carry so much. You can carry loads, but then actual load you can carry, payload is what we call, is going to be always very small fraction. So we have the data from all things now. Why this data is required is I will come back when you design airport payments now. We need the data of all the aircraft which is going to use a particular airport. Okay, because it is designed based upon the likely aircraft which is going to use that. So likely aircraft we have to decide. That means that SpiceJet owns them, or Air India owns them, or maybe some other company owns them, and then Indigo owns them. And we have to find out actually, that means what are the each trip which they are going to use now, which kind of aircraft they are going to use. And then like that, we have to find out summary of how many movements they are going to expect to be doing things like this. So all of them is going to be very difficult now. So in tons now, we can see aircraft can also have usually 350 to 400 tons, but it could be much more than that also. So if you don't really design properly, this can also happen. Okay, and then this can also happen actually. So that is one thing we have to really always remember now, because this is going to cause a damage to the, you can say, thousands or millions of dollars of investment on the aircraft as also on the runway, because runway becomes useless now. It is repaired actually. Even to take out this aircraft is going to be time consuming, and very few companies who can do this, taking out such aircraft without damage to aircraft, and then resurface this so that it becomes available. So that's why it is always very important. And please remember that the tire is definitely bald actually. Okay, that is what we are going to say. So last thing we are going to see is that what is the difference between these payment, which we say highway payment and airport payments. The airport payments generally require thicker payments, better surface materials due to heavy loading. That means the top surface layer is going to be definitely much stronger and stiffer due to heavy loading and higher tire pressures. Then the number of repetitions on airport payments is very small actually. We will come to that when we say design is almost negligible compared to the highways. And then load distribution, I have shown you the rutting and all. Basically, when you have your trucks going along a lane of 3.5 meters, basically we can see what the track, what the tread is going to follow. But in the case of aircraft now, it lands in all kinds of weather basically. So what's going to happen now? They are not going to land at the center line of that now. It may move this way, that way, particularly at the actual landing now. That's called wander. So it may slightly this one. You see a hit actually when once it touches the ground, and it's going to touch the ground around 180 to 200 kilometers per hour. And so it has to finally come to the center line. But before that, it wanders from slightly this side, that side, and then carefully maneuver itself now. In highways, the moving loads, loading duration important. Airports, moving loads in the interior and station loads at ends. That is very important actually. When you have a runway now, its characteristics are not going to be the same from this end to that end now. The ends are different and the center is different. And in some cases, the center portion of that runway is going to be having much thickness, that means cross-section wise, and edges may have different kind of thicknesses also. That you please see that. That means the end of runway, say 10% the ends, if you consider, let's say 1 kilometer now, so 10% of 100 meters either side is going to be of a different kind. Sometimes it could be 500 meters also. So it all depends upon that. The edges of the runway is one which is going to be more critical, and for the simple reason that actual landing is not going to be causing any damage to the damage to the runway. Why? Because it is still partially airborne. The entire load which you thought of is so many tons now is not going to land on the runway directly. It will be definitely partially airborne. That's why the turbines are still working actually. Okay, but the impact of that has to be borne by the obviously the aircraft itself. That's why the aircraft structure design is going to be very important now. So that is what we have to really keep in mind. And the load placement, same way, edge loading, interior loading, application theories is all going to be same now. So that is what we thought actually, that these are the basic differences in the number of movements and the weight and things like this, and the structure of the payment is going to be different, but the materials which are used actually is very similar. That's why we treat the payments together in the same way, but the authorities which are controlling the airports are different from the authorities which are controlling the highways and rural roads now. So we follow their code, their code practices, but starting from principles of what is the distribution, what is the elastic theory which we are going to use now, what is the basis for our present day design? Because unless you see the process of how they arrived at the modern methods now, we will not be able to appreciate why this kind of methodology is being adopted, and also you'll not be able to appreciate what is the way in which we can do research and then how to improve the system. So that is the basic summary of what we are achieved actually over the last 3 lectures. What is the overall concept we are going to think of now? Then we will go in details one by one. I think tomorrow we'll take up the issue of the materials very quickly, and then we'll continue for the next 3 sessions in different ways.